Okay, so now we're going to talk about market basket analysis. And this actually uses some of the principles when we talk about independence of probabilities that was used in the chi-squared test. But it's less of a statistical test and more kind of a mechanical sort of algorithm that searches databases and tries to find interesting rules. So let's define a few concepts. And this is in the notes, but I just want to kind of explain it a little bit more. So the first of these is support. Now the support is just the proportion of transactions that contain an item. So if 3% of if kind of 3% of shoppers purchase a particular item, then the support is 0.03. So let's just kind of have a simple example. So we say that support for Dr. Pepper is 0.03. So out of all these transactions, out of every 100 items, 3 of them are going to contain Dr. Pepper. Now, imagine that if 0.5% of items, so this is like 3%, if 0.5% of items included both Dr. Pepper and cheesecake, imagine that, having Dr. Pepper made you really desire some cheesecake as well. So we've got support Dr. Pepper comma, cheesecake. These kind of squiggly brackets, it just means a set. So we have 2 items in this set which contains Dr. Pepper and cheesecake equals 0.005, which is 0.5%. The next thing we define is this idea of confidence. And this kind of tells us how important our decision rule is relative to a baseline probability. So the confidence of x to y, which is almost saying the confidence of having y given that you have x in the basket, is support of both x and y. Going back to your basic business stats 1, remember this is an and. This means both of them in your basket. All over having x in your basket. Note, this is not symmetric. There could be like a lot of people who have Dr. Pepper and no cheesecake, but maybe nearly everybody who has cheesecake has Dr. Pepper. So this, okay, that's not going to happen in practice, but this is not necessarily symmetric. So in this instance, we have 0.005, for example, divided by 0.03, which is equal to 0.1667. Okay, let's go. Let's make it a little bit smaller and then go down a little bit. Okay, so my next little concept is that called lift. Now the lift is a measure of how much more than expected and this is like what I said was quite similar to how the chi-squared test works. Is the co-occurrence of items. Oh, I spelled that wrong, but never mind. So the lift is defined as the support for both between two items is defined by the support of X and Y all over the support X, support Y. And this is kind of, again, as I said, it's based on probabilities. Recall that if two items are independent, the probability that both of them happening is the probability of X times the probability of Y. So it might be that the probability of buying chicken is completely independent of whether you buy Colgate toothpaste. Probably not perfectly independent, but it's probably pretty independent. And the probability that you buy chicken seasoning is probably very definitely not independent of the probability of buying chicken. That probably is going to have quite a high lift. So all that is basically, if you take the support as like a measure of probability, it's just how much more than would be expected than if the items were independent. So if the items were independent, support X and Y would be support X times support Y. So you would actually get a lift of 1. So lift X comma Y is 1 if items are independent. Now imagine, let's go back to our example. So say, for example, support for cheesecake was 0.02, then the lift for Dr. Pepper and cheesecake is going to be 0.05, this kind of them both occurring together, all over 0.03 times 0.02, the individual supports of each item, and we get a lift of about 3. So there's kind of 8 times more likely to co-occur than if by random. So the higher the lift, the more likely the products are to co-occur. Okay, so what do we actually do with this kind of analysis? So this kind of association or market basket analysis. Well, basically, we're trying to find groups of items that we call item sets. So Dr. Pepper and cheesecakes is an item set. And we set a minimum value of support. So we find that have the following. They have support is greater or equal to some minimum level of support that we set, and have confidence greater than some minimum level of confidence we set. If we set these values too low, we'll just literally have thousands, if not millions, of item sets, and we don't have time to go through them. We set them too high, and we might just get very obvious things like toothbrush and toothpaste, and we might miss some interesting associations. So setting this is something of a trade-off. And the main algorithm we use is called the a priori algorithm. And the reason we need this is an item, each item might be in or not in an item set. So say we have a basket. So say we have 1,000 possible items. We have a choice. Each item can be yes, I'm in the basket. Each item can be no, etc. Now, it's unlikely that one person is going to put all 1,000 items in their basket, but it's still a possibility. In fact, if we have n items and we have 2 states per item, yes or no, we have 2 to the n possible item sets. So say, for example, Walmart has 142,000 items. We have, and I think I got that number actually from real world, actually a real number. And that's going to actually break R. So what the algorithm does is it basically removes a lot of item sets that are not possible. And to do this, it uses the a priori principle. Let's get a different color. And that basically just says that for any item sets, so for any item subsets, if X is a subset of Y, then this implies that the support for X is greater than the support for, greater or equal to the subset support of Y. So we know that Dr. Pepper is a subset of Dr. Pepper and cheesecake, so we can say that support, i.e. more people are going to have Dr. Pepper than both Dr. Pepper and cheesecake. Now that seems like common sense, but it actually helps us make, when we're searching for these things, it makes us a lot more efficient. And this is as far as I'm going to go with the algorithm, because this isn't a computer science class. I just wanted to have that kind of principle of how it works. In the notes, I link to some more advanced kind of notes on this, which won't be required for the exam. But if you're saying engineering, they'll give you a little bit extra. So if X is a subset of Y, support X is greater than or equal to subset Y. So in this case, support, sorry, I completely messed that up. So the support for Dr. Pepper is greater than the support for Dr. Pepper and cheesecake. So I had like Dr. Cheesecake there. I think this semester's getting too much for me with my Dr. Cheesecake. Okay, so that makes a lot more sense. That Dr. Pepper is a subset of Dr. Pepper and cheesecake, thus it has greater support. Okay, so now on to kind of the R part. Okay, so we're back. Now we're going to actually do the association rule algorithm in R. Now, we've got an example data set called groceries, and this is like a really simplified example. There's also a more complicated one that I've done in the homework. And in this example, you see that each shopping basket bought by a person and recorded includes all the items that person has bought. So we have the first person bought citrus fruit, semi-finished bread, margarine, and ready soups. The next shopping basket was tropical fruit, yogurt, and coffee. It's literally the item name in kind of double quotation marks with a space bar between, with a space between. So very simple format. And we're going to use two libraries. We're going to use A-Rules and A-Rules-Viz. A-Rules does the association rule mining, and A-Rules-Viz has a few graphics based on that. So let me run that code. So we've loaded things. Now let me basically, when you read in this file, it's not a CSV file. So from the A-Rules library, there's a function called read.transactions, and that will load in the groceries. And there's a function called inspect that lets you look at the association rules. So I'm going to inspect, and I'm going to do head. Head basically is the first 5 lines. So it works in exactly the same as the data frame, and expect allows me to view them. So here I've got basically what I showed you in the text file, but in a slightly different format. So the shopping basket 1 contains these items. Shopping basket 2 contains these items. Now, the A-Rules-Viz has a few plots. Now, just as a... So if we just type in like R, A-Rules, we get the instructions, and we can find out the features and any parameters and examples. So again, this is kind of really helpful for you guys. So R, A-Rules-Viz, A-Rules-Viz. And so each of the functions, so we go down here, and we've basically got all of the different functions in A-Rules-Viz. So we have like the plot, and it tells you how to plot the different rules, and also the different options in plotting the rules. Okay, so back to the code. We can run an item frequency plot. And this just tells us the most popular items in the thing. So we have like 2,500 of the transactions have whole milk, which is the most popular item, followed by other vegetables, rolls, buns, and soda. Now we're going to run the a priori algorithm. And it's just literally a priori. And then we have, I told you this algorithm chooses all the item sets with a minimum value of support and confidence. So we set these values here. We can play around with them quite a bit. And, what will give us the best set of rules. But again, it's this trade-off. The higher the weight we make these items, the smaller the number of frequency sets. So this tells you a little bit about it. It tells you how long it took, how many items we've chosen, and how many rules. So we have 120 rules here. And inspect, we can then inspect, and we can actually inspect the output. So we can look at the first 20 rules. And let's make this a little bit larger. And you can see here we have the rule. So here we have baking, we had X to Y. Here, baking powder is X, and whole milk is Y. So we find that baking powder and whole milk are brought together, possibly because these are the things you need for baking recipes. And we can see the support, the confidence. We actually have the lift. So this has a lift of 2. So this is, twice as common as if these guys were independent, and the number of times it occurs in the data set. And we go through all the different rules. We also have different ways of selecting this. We can, for example, choose all the rules with the lift of 3. So all this says is the subset command basically says we're going to take a subset of our rules, and we're only going to choose them with lift is greater than 3. we could do something similar for confidence. We could say, hey, everything with confidence greater than, 0.6. So here we go. Here's the lift. And we have all the rules. And there's one, I think we've chosen this one that has a lot of items, so it goes on to the next line. But you can see all of these guys have lift greater than 3. It gives the count, and then it gives the actual left-hand side and right-hand side. And most of these are kind of other vegetables and how they combined. I guess you could almost do these in terms of a promotion for recipes. But do remember, this is kind of a small illustrative data set. It's not a real-world data set. And what we can also do is we've got the subscript command. We also have the sort command. And basically, we're sorting all our rules. We can say decreasing true or false, whether it's increasing or decreasing. But generally, we want the highest one first, followed by the next, say, the next ones going down. We do them by confidence, and we choose the top 10 rules. And here we have the top 10 rule. There we have the rules sorted by confidence. The highest one's got a confidence of 0.7, and the 10th has got a confidence of 0.62. And these seem to be mostly ones involving whole milk. We can plot them. There's a plot command, which is I just showed you when we went on Google. Let's just move this. And this basically has my different rules by all the ones selected by support and confidence. So you see the minimum support is the minimum we specified for the algorithm, 0.005, and the minimum confidence again is 0.5. And we actually have an interactive version. And what we can do is we can select a rule, say, hey, this looks an interesting rule. It's got pretty high support and confidence. And then we're going to click inspect, and we actually see the rule appear on our screen. So we can actually go through and check the different rules and just examine the rules a little bit more closely. Now that's it. Apart from the fact that I've been a complete idiot and I realized that I've included partially the answers to the homework in the code. I forgot to remove it. But that will have to, I can't, as it's been up for a while, I can't remove it now because some students might have seen it and some students might not have seen it. But yeah, I've been a fool. But that should actually be a good thing for you guys. Okay, so thanks a lot. And that's the lecture.